and we have to do that of the yard piping, the vessels that are involved, the instruments, the compressors, and because of that, it's a collaborative effort between the process group, the piping group, and the rotating equipment group, and sometimes the instrumentation if we have to move things like PSVs or other instrumentation location. And this is a computer analysis which takes a look at the exact piping layout of the facility. It's not a theoretical model. We actually have to have the exact piping that's being done. And the vendors that do that, they'll put that into their computer simulation, and then they'll run the compressor operation to see what kind of harmonics are caused and at what location high pulsation pressures are found. And in some installations where this is not done or where it wasn't done quite accurately, there have been PSVs that happen to be located right on a high pressure node. And so at the exact same frequency of the compressor, the PSVs would pop off and release gas into the flare header. And so that became very disconcerting to the operations guys because the PSVs are never supposed to be popping off, and to have it going continually, they figured that the PSV was obviously had a problem. So they shut the process down, depressurized it, changed the PSV out, started back up again, exact same thing. And it wasn't until they actually ran the acoustic analysis to find out what the problem was and where to move the T for the PSV off to get it away from this high pressure node that they're able to actually get the system to operate without a constant PSV chatter. Now these are pulsation dampers. There's on the suction side, and underneath you just barely see them. They're on the discharge side. And this is the first line of defense that we use to try to contain all the pulsations that come out of the reciprocating compressor. These are sometimes just big volume chambers. Sometimes they will have barriers and choke tubes to try to tune the natural response of the gas passing inside to coincide but be out of phase with the gas compression frequency of the compressor. And we'll do that. That's how we try to keep the pulsations internal to the machine and not escape out into the yard piping. These are custom designed for each installation. You can't say that I'm going to change the speed of my machine or I'm going to change the flow rate or recylinder it, and then you expect to use the exact same cylinders. All that has to be done as a custom job. In very high pressure applications, these in Boca Raton went to 12,000 psi. We have spheres because this is the only thing that will really contain the pressure effectively for the same material.
So what will happen if I have some solid on it?
You have some solids in the gas stream?
Yeah, I need more than 12,000 psi. You can't use the reciprocating in the case.
If you need to go above 12,000 psi, well then you would end up using a different style of recip, but you would still end up using a recip. Be a much more.
Use a piston type thing. The piston might broke.
Well, what ends up if you have extremely high pressures, the actual compression port of your piston is this big, but the torque transmitting is that big. Okay, so they do it, and it's a big, massive machine. It's a huge frame for a very low flow rate. But that's because you're right, the internal forces are tremendous. Recips require a very large footprint, and they're high maintenance items. And one reason that they require a large footprint is that while this is the size of the compressor, if you ever need to do maintenance, you need to be able to pull this entire rod out over here. So you can't have anything in this area that would preclude you from being able to pull that out. The other reason why they're high maintenance, on a centrifugal compressor and the axial compressor, there's two bearings, one moving part. For example, this is just a two-cylinder compressor. There's 1, 2, 3, 4 main bearings on the crank, then 1, 2, 3, 4 bearings on the connecting rod, and then you've got a sliding motion bearing on the crosshead, and then a sliding motion at the piston. All those are wearing parts. Then you've got a sliding action on the packing, and a sliding action on the wiper, again, which are all wearing parts. So there's a tremendous number of parts that are wearing out inside this machine, plus then there's the valves. This is the piston, these are the compression chamber, the valve locations. This is what's known as the high pressure packing. This is what actually contains the gas inside this section of the compression casing. Now the gas obviously wants to escape out along the shaft to the lower pressure of the atmosphere, so this requires constant adjustment so that it's in sufficient contact to prevent escape, but not so tight that it gets extremely hot and then wears quickly. So this is a constant maintenance item. There's some wipers here and here, which while not as critical also require constant attention. But the biggest maintenance item are going to be the valves. And that's what these are. Basically, they're just a series of check valves. But they're designed for extremely low pressure drop and relatively high flow rates. And so this valve here, this is what's known as a plate valve. And right now it is in the closed position. It covers over the gas passageway from the underside. So there's springs in these chambers which push that valve into that closed position with a minimal amount of force. Now for this valve to operate, the pressure on the underside has to be high enough to overcome the spring pressure, at which point this valve picks up. And then the gas flows through the slots in the valve out the discharge side of the valve. Now, there's not a lot of room, and because of the speed of the gas passage, it's not a nice, gentle transition from the closed position to the open position. It slams on both sides. And so because of that, you've got whatever frequency the compressor runs at, this valve is slamming open and close, open and close, open and close every time. And so because of that, there are very high stresses. If there's any dirt or particles inside of there, it becomes a stress concentration area. These valves have a finite life. You will start to have cracks in them. There's no getting around it. And the crack will propagate to the point where a section may fall out. So these are the highest maintenance items on the machine. Talking with the operators and the manufacturers, if you get 9 months of life out of a valve, you've done really good. Some people claim that if you don't have any process variation, it's an extremely clean process, you can get maybe a year. And that's just to replace a valve. And you take a look at, on each cylinder, there's a minimum of 4. And on some machines, there's up to 16. Every time you crack a valve, you've got to shut down and replace it. So that means quite frequently you're going to shut down a machine, replace one. A week later, you're going to have to replace another one. A week later, you have to replace another one, which means, of course, you have to shut down your process, blow down your process loop, come in, do your maintenance work, a couple hours to replace the valve, and then repressurize, and then get back up online again. Rotary compressors are another form of positive displacement machine, but they don't have any valves like a recip. Therefore, they have fewer things to actually go wrong. This is one form. It's called a twin lobe blower. Process gas comes in at suction pressure, fills up a chamber. These lobes rotate against each other. And when the tip of this lobe comes over to this casing, it traps this process gas in this chamber. And then as the lobe rotates, this chamber then opens up to the discharge side. Now, the one drawback on this compression set is that while this gas is trapped inside this area, there's no compression actually taking place. It's just being closed off from this side and then opened off to this side, which means that you've got high pressure gas here, low pressure gas suddenly opening up. This gas backflows to compress the gas inside this chamber, and then the lobe continues to rotate and pushes that gas out. So this is a very noisy operation, and it also will impart pulsation into your downstream process piping, not as much as a recip, but it is a concern that you may have to be aware of if you have a very large or high horsepower compressor. This is a different style of rotary lobe machine. This is called a screw compressor. Pretty obvious why. You've got a male and a female helix, which are counter-rotating against each other. Very close tolerances of machining inside. Suction pressure gas enters on the one end, and the nice part about this machine is that as the helix is rotated, it closes off the gas from the suction side before it opens it to the discharge, compresses the gas in an axial direction against the distance wall, and then it'll open up to the discharge passageway when the design pressure is reached. So if you're at your design point, this is an extremely smooth operating machine. But as you get away from your design discharge pressure, it becomes very noisy for the same reason. If your process pressure is lower than design, then the gas is going to have a sudden escaping pulsation. If your process pressure is higher, then it'll be pulsation into the compressor before it gets pushed back out again. So these will handle light mole weight gases. They have pretty decent efficiency. Again, they just have these two moving parts, no valves, so they're a much more reliable form of compression than a recip. They don't have the same pressure ratio, so they're only good to maybe 900 or 1,000 psi. They also have 4 sets of bearings and 4 sets of shaft seals, and so these may have slightly more gas leakage to the flare system than a recip might have. This is a screw machine that we bought and installed. It's a top suction discharge, bottom discharge. You can kind of get a feel from this slide just how much extra stuff there is around the equipment to make the equipment operate properly. You're going to have lube oil systems, seal systems, all going to the compressor, and then you'll also have the electrical components, junction boxes for heaters, instrumentation, all surrounding the equipment, all on the skid, which sometimes makes the actual compressor kind of hard to see. This has a gearbox on it with its instrumentation, and then there's a motor driver. When we installed this, I had the hardest time trying to figure out what this big old box was. And then I suddenly realized this is the terminal box for the power cables for the motor. It's physically bigger than the motor itself, and it has to have its own supports because it is so large. When we went out to buy this, the electrical group asked for the largest terminal box you could get, so that it made it easy for them to mate up these very large high amperage cables. And the motor vendor took them at their word, gave them the largest box off the largest motor that they made, and sent it out. It's a significant overkill, but the electrical guys loved it. It made make up connections really easy.
Is there any specific reason that it's not bolted on the actual foundation?
Well, this is actually on the skid, so it is being supported off of the skid. So that it's shipped this way. We have the extra timber in there to support it during the transportation, and then all that got taken away. The actual motor itself terminates here. This back section here is acoustic enclosure over the fan to try to keep the fan noise down to tolerable levels. The client wanted 85 dBA, and so we had to have the fan good for about 82 to meet his noise requirements. But you can see here's the terminal boxes for the space heaters and for the RTDs inside the winding. Reasonable size. Adductors. P&ID symbol for them. They have, like we said, they've got kind of a niche service. They use high pressure, high velocity motive gas to create a localized low pressure area inside, so that it can go ahead and pull low pressure process gas to this lower pressure area, and then the velocity accelerates it back up to the final discharge pressure going to wherever it may have to go. We use these on sulfur pits to be able to keep the sulfur pit at either atmospheric or slightly below atmospheric pressure, so you don't have the sulfur gases constantly coming out to the atmosphere. Sulfur loading stations, you'll see these so that they will be pulling sulfur fumes out of the trucks that cart it off, so try to keep the sulfur fumes out of the atmosphere. And we may use one of these on Melanie Point as a backup to a compressor. If the compressor goes down, we need to get the gas into the flare, and so we would use this to boost it up a couple psi to make sure it gets into the flare. Compressor seals. Originally, there was an oil film type of a compressor seal. This is kind of old technology, but they're still in use, and so some of you guys may run into them on revamp type work. But what they do is you've got your process gas over here and your atmosphere over here. You inject an oil at a pressure actually higher than your discharge pressure of the compressor. And what that does is it allows the oil to come across this small annular section and into this drain. By having the oil flowing against the process gas, it keeps the process gas inside the compressor. And then coming down this drain is a mixture of process gas and oil, which has to be handled. Across the other side is just going down to atmosphere, and so this is called the sweet seal oil, and it'll just go back to its regular reservoir. Contaminated oil, usually called the sour oil, this will go into what's called a degassing tank. And with the degassing tank, we'll have a heater in it, an agitator, to try to boil off any of the entrapped gas inside the oil, and then send that gas to a flare system where it can be burned, and then the somewhat cleaned oil goes back to the reservoir to be reused as sealing oil. This is the seal oil system for these compressors. Because these are injection machines and they had pressures up in the 4,000 psi range, the oil had to be capable of going up to 5,000 psi. We had a reservoir. We've got 2 sets of pumps. We have coolers, control valves for both temperature and pressure, control systems, monitoring systems. It's an extremely complicated system. It takes up a lot of floor space just to keep the seals supplied with oil for these compressors. Nowadays, we use what's known as dry gas seals. We use 2 different styles. One that's called tandem, which is actually 2 seals in series. The inner one contains the process. The outer one is there as a backup in case this one should fail. The other one is called a back-to-back seal, where you have a process gas that you just cannot allow to get to atmosphere, either a high H2S or a chlorine, some kind of a toxic gas. And what you have is you've got a nitrogen or some other inert or process benign fluid injected between the 2 seals that's at a higher pressure than your process. And so that benign fluid comes across your seal face and into your process. By having this at a higher pressure, you'll ensure that your process gas never escapes out to atmosphere. If there's a seal failure, the gas will still be higher. You'll just use more of it, but you'll also get an alarm knowing that something's happened to your inner seal. The way the tandem compressor or the tandem seal works is that you've got clean process gas coming across the inside back into the compressor, and that's to keep the seal faces cool. It's also to make sure that any dirt or debris, fluids, don't work their way along inside this labyrinth and inside this chamber. These surfaces are very intolerant to contamination. There is a small amount of gas that does migrate across these faces because this is spinning and this is stationary, and we don't want to have them in physical contact. We want them lifted just slightly to minimize the flow rate, but to make sure that they aren't physically in contact so there's no wear. So there's a small amount of gas migration across this seal face. We inject nitrogen at this point between the two seals, and that nitrogen injection, along with this process gas, is forced out to flare on this interseal chamber event. So this part of the seal is saturated with process gas. This part is saturated with nitrogen. The mix goes out to flare, and then a small amount of the nitrogen gas goes across the outer seal face, and then goes out to vent to atmosphere. Sometimes we'll put in what's known as a tertiary seal or a catastrophic failure seal, and we use that with a nitrogen or air purge on it to keep oil from the bearing from migrating along the shaft and trying to contaminate the outer seal. What the seal face looks like is you can see that it has a kind of an interesting an interesting pattern etched into it. This pattern is only a couple of thousandths of an inch deep. You really can't feel it. All you can do is see it. And what happens is the gas that's on the outside diameter of the seal gets trapped inside this small etched surface, and the rotation of the shaft and the friction between the stationary and the rotating part causes this gas to be pushed towards the inner edge of the seal face. Once it gets down there, it can't go any further. All it can do is build up some pressure, then that pressure is what separates the rotating face from the stationary face, and that separation causes a small amount of the gas that's being built up in pressure here to flow to the inside diameter and then across the seal face. And this is what it looks like in real life. You can see it well, but you can't. It's such a small etching that it's very difficult to feel it. And we talked about there's a very sophisticated sealing system that goes along to support these seals. You have processed gas coming off of the compressor, which has to be cleaned up, filtered, and then re-injected. You have nitrogen that's coming in at certain pressures and flow rates to be able to make sure that the processed gas across the inner seal doesn't migrate towards the outer seal. You have a series of instrumentations monitoring all these flows and pressures to alert the operators if there's a problem. And then you also have a lot of different areas that are going off the flare in case there is a catastrophic failure. So that is it for compressors. We'll start in on drivers. Let's say we take a 15-minute break, come back.